Now you see the model predicts properly, like which helps in improving search engine ranking. Our responsive web design ensure and offer less distance accessible. And if I go to this website, you can see which helps in improving search engine ranking. Our responsive web design and ensure and effortlessly accessible. So it's predicting properly what's come next. Okay. Hey everyone, this is Abdul Sami, your AI engineer. And in this video, I'm going to tell you how we can build the LLM from scratch. And this video will be really, really important for everyone, of course. And because for this series, what we are going to do right now, and this will be the last part of this series, the LLM series, and then we will move forward to other things. And in this video, I'm going to tell you how we can build our own LLM model from scratch, what you are seeing on your right side. So first of all, let me tell you agenda of this video. First of all, I will let you know about the tokenization, then attention mechanism, then transformers, then model training, and last one will be your the final output. So the how many before going to the this LLM stuff, I will let you know. You have to know basically the types of transformers. Transformers. So there are actually three types of transformer. One is the encoder model. So this transformer architecture mostly used for in the BERT, Roberta, like the sentiment analysis, okay, kind of stuff. And second one is the decoder transformer architecture. And this architecture mostly we are using in the GPT model, like the OpenAI, like build the GPT, like Anthropic, generative pre-trained models. And the third one is the encoder decoder architecture, this one, and mostly we are using for the machine translation kind of stuff. So in this video, we are going I'm going to basically tell you how we can build LLM like GP, like decoder model from scratch. So in decoder model, let me tell you how actually is it working, decoder transformers. So let's suppose you have a three words, I like pizza, and the vocabulary size is also three here because there are three words. So let's assume the vocabulary size is three. So let's suppose I pick first letter I and I inject into the model, and the model predicts a three output. Just because the vocabulary size is three, so model will predict the three outputs. The first output will be like 0.3%. This is the probability, 0.3% model thinks the like model thinks 0.5%, like after I it should come like, and pizza model thinks yeah pizza 0.2%. It should become after I. So because the like probability is high probability, so we model pick the like word and give us return as an output. And now we are going to pick two words I like and sending into the model. So now model again predict the three outputs, and depending upon the highest probability we pick the pizza keyword, and at the end our output will be the I like pizza. So just to let you know about the things, okay, let's suppose if we have a big sentences in like in the OpenAI have built the GPT model, GPT 3.5, 4, and Anthropic has built the cloud model. So there you can see they have a very big context size, context window. So here vocabulary size is 3 and the context window is also 3, we are assuming. So that's why model is predicting 3 word according to the vocabulary size. But if model vocabulary size is like 10,000 words or 20,000 words, so model is going to be predict 20,000 words at a time. And the highest probability word we will pick and put it like this is what comes next. Okay, so this is how the decoder architecture work. Like the GPT, how it's giving you a response like the token by token. Hi, how can I assist you? So of course, model first model give the model hi, and model say okay. After hi, I have to say how. And when we model give us a how, then we put two words, and model say how can. And this is how it's working as I explained to you here. So first, as I explained you, first thing will be the tokenization part. So in this architecture, what we are going to build. So in terms of tokenization, we are going to use byte pair encoding model. Byte pair encoded transaction were initially developed as an AI as an algorithm to compress text basically. Okay, and that used by OpenAI for tokenization when pre-training the GPT model. And it's used by a lot of transformer model, including GPT, GPT-2, Roberta, BERT, and Debugging. Okay, and there are a lot of other types of tokenization as well, like world pieces, Unigram. Okay, so but we are using a byte pair encoding for this video lecture. So basically, how okay, let me write a coding how actually it will work. You don't need to build something from scratch, like because there is a pre-trained stuff is available. Sorry, pre-libraries are available, so we are going to pick one of the library. like the tokenizer library. So in tokenizer library, we have to first define an object of tokenizer, and we are going to pass a BPE object inside it, and we are going to put the pre-tokenizer is equal to white space. And after that, we are going to define the pre-BPE trainer class, and in that stage, you can see the vocabulary size equal to vocabulary size minus 5, because we have five special tokens here. Special token means I will explain to you later in the next video what actually is the meaning of special token, because we are only training a base model right now. So when it comes to the chat model, then I will let you know for the special tokens. So we are also going to add special tokens there. And then after that, of course, text list is equal to the list of text. So list of text means we have a lot of chunks of corpus of text from all internet. But in this video lecture, I have scrapped already the one website from internet, one company website, basically Cortex Soul. So basically, I'm using that website to train my model on that specific website. So this is what how we have like we are going to put all the text in this train from iterator method, and we are also going to put trainer like the BP bits by byte pair encoding, and at the end our tokenizer has been trained. So once our tokenizer has been trained, so we are going to define the two functions. One is, as I explained to you in my previous videos as well, model does not even understand the text. We need to convert the text into the numbers. Okay, so for converting a text into the numbers, we are going to define that encode function which returned us tokenizer.encode. We are going to put text and it will return us a unique IDs. And then the decode function will convert those text into numbers into again a text. So this things has been done. And after that, we need to define a data set, the class in which we are, of course, we have a lot of data. So we need a class which process all data. So you can see in the first line, self.data is equal to toy.tensor. Because our all the data is like in numeric form, as I explained to you after encoding. So we need to convert into a tensors, because of course for the GPU training, we need to convert all our numeric data into tensors. And then of course context length. Context length is a window frame of our model. How much the text model we need to put at one time. As in GPT models, there are like 8,000 context size of a window. Some is 16,000 context size of a window. Like how many words model can get in the one time, the maximum amount of words. Okay. And then there is a def underscore underscore get item. That's of course a function. I'm going to override it. And you can see there are X and Y values. So in the decoder transformer, as you understand, as I have given you example previously, so you can see X is equal to self dot data ID, like this is the index, plus self the context, how many length is. And then in the Y value, I am just passing plus 1. Let's suppose if I say there is a I like pizza. So if I pick I word, so the second word like, that will be the output of the that like the word. So if I give two words to a model I like, then the third word pizza will be the output. So the next word basically actually the output. So our model task is to predict the next word. Okay, so that's why I put in the Y. Y is basically output IDX plus 1. So whatever the input is, the next word will be the output. So I hope so you understand this point. Now it's time to prepare our data set. As I explained to you, we have a lot of text data which I have get from one of the website on the internet. So we need to convert that data into numeric form. So we are calling encode function, and we are passing this text value, and we are getting encoded text data. And then we are splitting into test and validation data, sorry, training and validation data. And our train size is 0.9, like 90% training data and the 10% validation data. I will explain everything, like I will write everything in our lab as well. So I will show you there after this presentation, okay, theory presentation. And then after that, of course, I have already made a text dataset class where I'm going to now pass the train data plus context length, validation data plus context length, and then there is a data loader. So this is the PyTorch built-in data loader which we need to which we are going to use, and we are passing a train dataset and then the batch size. So first, we are not going to put all the data for a training, for we need to split into the batches. So accordingly, it will also speed up our training process as well. So after that, of course, now the second part will be the attention mechanism. So now we have prepared our data set. The first part is done. We collect the data. I have already collected it, so I did not do it here. And then I convert data into tokens. Done. data set preparation part is completed, and then it's come to the attention mechanism. So now I'm going to tell you how we can do this self attention mechanism part. So I have already explained this self attention mechanism in my first lecture of the LLM series. If you still want to dive into detail, go and watch it and come here back. Okay, come back here. So then, of course, first of all, I'm going to define a class head. Head means a self attention. I just rename it, okay, differently. And we have a three thing: key, query, and value as well. Okay, we define three weights matrices, and then whenever the input is going to become, so input is first of all doing the matrix multiplication with the key and query, as you can see in the diagram as well. And after doing this matrix multiplication, we need to calculate the attention score. So for calculating the attention score, what we are going to do, we are going to do the matrix multiplication of the query with the key transpose. Okay, and then finally we are going to apply softmax and get our weight matrices. And finally, what we are going to do, we need to apply attention to the values. Okay, and finally we get the z score, the attention output score. Okay, so this is how is it working. So if you still don't understand, please go and watch my first video so you understand about how actually the attention works and what actually the attention is. I'm not going to explain here again. Yeah, it will again, the video will be very long, so that's why. Okay, after self attention, we need to make into a multi-headed attention. So even you can see in the right hand side, there's a diagram like the mask multi-head attention. So in the diagram, you can see this is not a single self attention. This is not a simple self attention. This is a multi-head attention. So how we can make the multi-head attention block? That's the point. So first of all, we need to define a clause. So in the clause, there is the self dot head is equal to nn dot modulus. So and we are using a for loop function here. In the for loop, we are passing a number of heads, and then there is a for loop will run to the whole, and every time it makes a one head object. If you can see head into the head of size, okay, and then there is a projection there. As you can see, this is the for loop. This is a forward function. So of course, this is a for loop. So whenever we pass one input, so if there are 10 heads, so it will give me a 10 outputs value. So I need to concatenate it. So that's why I applied torch.cat function. And once I concatenate everything, then finally, of course, there will be a projection like a simple linear layer which convert this thing into a flattened stuff. And finally, we get the output. And after that, we there is a feed forward layer. So you can see this is a multi-head attention block. There is a add and non block. I'm not building this whole architecture right now. I'm just building some specific blocks. Okay. Now the multi-head attention block is done. The second is add and non block. Normalization block, this is simple here. I will add later when I am making the full block. And the main thing is the feed forward block. So here you can see this is a class feed forward layer which I have made it right now, and it's very simple linear neural network. So you can see simple NN dot linear, simple linear like dense network in the transformer, and then there's a ReLU function I am applying, and then finally we are getting the output. Okay, and this is a simple step. So after multi-head attention, now I'm going to make this full block. Even if you can see on the right hand side, there is a diagram. So in the diagram, there is a block where which has like multi-head attention, add norm, feed forward layer, and add a norm layer. Okay. So we already have built a multi-head attention and feed forward networks. Now we are going to combine into one block. So in the block, if you can see, first of all, we have self dot attention is equal to multi-head attention. Second thing is about the feed forward layer, and there are two layer norm. Here you can see first layer norm and second. There are three stuff. So just remove one thing because I'm only keeping two one. I'm only keeping the first one, mask multi-head attention. I'm not keeping the second one, and I'm keeping the third one, the feed forward layer norm. Okay. So as you can see, first of all, whenever there is an input is coming in forward network, okay, so it goes to the self.ln1, the linear norm one, and then it goes to the attention block. And after that, then we are going to use x plus. And why I'm going to use x plus, input plus self dot attention? Just because in attention mechanism there is a lot of commutation, multiply, there are multiple attentions, multiplications, a lot of stuff. So I also need to like models should remember everything. So just because there is a chance to loss of data, so avoiding the loss of data, model remember everything, I'm going to add x plus self dot attention. Okay, and then the second layer is s is equal to x plus self dot feed forward. So you can see in the second block there's a feed forward layer, but first of all I'm applying a non ln2, the second layer, add and non. Okay, add and non self dot ln2, and then I'm applying a self dot effect, the feed forward layer, and you can see this is a full block. what I have written here. And in the next here, I'm going to know make the small language model, because of course we are not making a full big large language model. We are making a small language model because that's for the one website. Okay, so it's same. The architecture is the same, just it's depend upon the data. So that's why I name it to a small language model SLM. And here you can see first thing we need token embedding. Second thing we need positional embedding. Third thing we need the block. Fourth thing is linear, linear. And five thing is LM underscore head. That's about where which give us the probabilities. And then in the first thing we are going to input. We are passing an input in the token dimension. You can see here what we are going to do in the diagram. We are passing an input in input tokens. And then don't worry about this output embedding what's written in the diagram. Forget about it. But this is actually we are passing an input. And then we are passing the input in the positional embedding. As you can see, the second thing is about the positional encoding. So what we are going to do, we are passing input we are making a positional embedding, because when there is a big paragraph, so of course model should know where the word stand is. Okay, model should know the position of the word, so it's easy for the model to understand the prediction what comes next. So that's how we are also adding positions. And then after that, we are passing this input in a block. As you can see, there is a block as well in the right hand side. Okay. So in this block, I am passing this input and it will give me at the end one output. And once we get output, we are passing into this linear layer and then applying a software at the end. Same goes here. I just passing into LM underscore head the linear layer, and then finally when we apply a softmax, we will get output. And at the end, this is a function. This is a code. If target is none, loss is equal to none. Else, I'm calculating a loss. And at the end, I'm returning logistic like the number of outputs, how many I get. Like it depend upon the vocabulary size. As I explained in start of the video, logistic. How many logistic is depend upon the number of size. Like how many values model is predicted, and at the end, it will be a loss. So that's it. And now I'm going to move to the coding part to show you how actually it will work. Okay, so now this is the time to write a code and do that stuff. I have already written the code, so I will run it. I have already explained all the code in the presentation as well, but I will run it to show you how actually it will work. So and this is your task as well. You also have to, scrap the data from any of the website, and using this code, you have to build LLM model. Okay, and also post on the LinkedIn and also mention me there. Okay, we have watched a video. I have watched a video and I have done this, and this is my output result as well. So in case of any question, anything, you can come back and ask me. I will respond to you accordingly. So I use this kotechdev.com website to scrap all data from all their pages like Shopify web development, everything from there. Okay, and at then I put it in input underscore text.txt file. You don't need to pre-process the data. Simple, just scrap it and put it here. You can see simple scrap and put it here. This is input underscore text.txt file. So first of all, I'm going to run this cell. Okay, after running this cell, there is an embedding dimension. So I just put embedding dimension is a 128. This is a hyperparameter. Vocabulary size is 5504. Okay, so in your case, you can see what vocabulary size will be the best for you. On my case, I thought, okay, 5000 is enough for me. Context length is a 250. So I just keep like model can in maximum model can keep 250 words. Number of heads, I just put the 12, number of layer 24, the batch size, I just say 64, and there's a CUDA. And then of course, after running this, you can see this is with open, I'm going to open the file and I'm just printing first 50 values. Okay, and this is the text length 55,450. So how many words I have? 55,000 words. Okay, my length is okay. And then I'm going to run this tokenizer part, which I've explained to you there. And after doing this, now I can call in code function to show you how actually it will work. Okay, let's say hi. I said say okay. Let me copy something from my data. I said say context us portfolio. Let me copy these three words and let me off this, and I'm going to encode it. And you can see contact us portfolio and it gave me a three different outputs. Okay, this is how it convert into numbers. And if I pass all three outputs back, 859. Okay, let me one pass one, and you see this is the context. This is how can revert it back. And if I copy this and pass this here, and you can see context as portfolio. So this is how we can encode and decode it. So our encode and decode thing is working properly. Here, this is all the code I've explained to in the presentation. So that's why I'm not explaining it here. So let me just run this cell. Okay, so our trained data set is 58,577 and validation data set is 6,287. That's okay. And this is the get batch function, which which convert my data into the batches. Okay, and then here is a head class which I've already explained to you. There is a multi-head attention. There is a block, and this is a small language model. So all thing is there. Okay, nothing. And now you can see this after running this class, there are some other save model. I have written the code there, and then here I'm going to train my model. So I'm just what I'm doing. Let me show you here. Model is equal to small language model dot to device. I'm putting into the CUDA, and then optimizer. I'm using a torch the Adam optimizer with the learning rate of 0.0001. Okay, and this is what, and here you can see this is all the code in the presentation I have shown to you, and here I have put the generate method. So this method I will use after the model will be trained. I will use this method to check the outputs, how model is performing. But before that, can I check right now how actually model is performing before training? So let me copy this thing because this will help me here. Okay, in code, I'm going to in code read the case study. Okay, let me copy something on the website. So it's good. Responsive design, not only, okay, let me copy this thing. Oh, actually, model, let me copy this line. And I'm going to put it there. Okay, let this. Okay, just I'm going to copy some of the text and see how model is predicting. I'm converting into torch and using a model, not a new model, because this is a model. And this, no, this model is not trained. Okay, I'm going to model or generate. I'm running this function. I need max 100 tokens, next 100 word predictions. Okay, and this is the context. What is the context? So simple. I convert this torch into tensor. Sorry, I convert this numbers into tensor. As I mentioned to you, this encode function give me a convert a text into numbers. So I need to convert these numbers into tensor so it's run on the GPU. So this is how I'm applying here with the toy or long and devices CUDA and final how's the model will generate output. And this model is not trained yet, and it will simple generate some random stuff. I'm pretty sure. Okay, so it's generate 100 tokens. I should need to maybe convert 50. Gotcha. Okay, let's see how much time it will take. Okay, so you can see how what is generated. Responsive design not only meets user expectation but also receive MENTs, enhancing relationship, NCMS, third uncompiled, incomposed, presentation, trending. So it's not properly in the evaluate either practically model scaling because model is just random, it's random stuff. It's predict 100 word, but it's totally random because it's not trained yet. So because this is two functions, that save and load function, load model function. Save function means it will call once a model will be trained, I need to save it, and load function means after training, I need to load a model to for prediction. So that's why I made these two functions. So now we are going to train model.train. Steps is 2000. I'm going to train up to 2000 steps. For step in the range in step x comma y get batch. So I'm getting a one batch. I'm converting it to x.2 CUDA. Like I'm putting inputs into the CUDA. Same for the y.2 as well. I'm putting the outputs onto the GPU as well. And then I'm passing those values into x comma y into the model. And model will generate two outputs as I explained in the presentation as well. Logics and loss. And then I'm going to apply optimizer dot zero grad loss dot backward optimizer dot step. Like I'm doing the back propagation, calculating the after loss. And then if after 100 step, I'm printing how many steps and what will be the loss. And after 1000 steps, I'm saving my model. So let me run it and it will take 10 to 12 hours. So I'm not going to train all the things right now, okay? But yeah, after like now I'm going to stop it because I have already trained it. So just to show you, you see saving model as step 0, loss is 8.808025, step 0, and let me check after 100 step how the loss will be decreasing. Okay, so like after 100 steps, you can see the loss is like 3.69. Okay, so after 2000 model will be properly trained. Okay, I just stop it because I have already trained it. Okay, so just to tell you one thing, okay, because one stuff when you are working with a pre-trained model, you don't need to put a special token, and you have to just comment this line, and the vocabulary size just make it to like 1500. Okay, I just change it to just because this hyperparameter I just also made for my fine tuning model, so I just convert it because just to let you know where if you are following this video. So you have to just change this thing and remove this stuff as well. Okay, then it will work properly after training. And once it's properly trained, okay, now I'm going to loading checkpoint is equal to touch dot load, and I'm going to path this path with the map location is equal to device and weights only true. Okay, with the 2000 step and model dot load state simple, because this was my model class. So simple dot load weight. So once I load weight node, the model weight will be from the when I train the model. So when they pass now this responsive design does not meet user expectation, but also receive Google Mobile Friendness badge, comma. Now you see the model predicts properly, like which helps in improving search engine ranking over responsive web design, ensure and offer less distance accessible. And if I go to this website, you can see which helps in improving search and ranking over responsive web design and ensure and effortlessly accessible. So it's predicting properly what's come next. Okay, so let's copy something different. Okay, let's move to okay at the end. Okay, let's move. I'm going to copy this. We are using to create flexible layouts. Okay, and I'm passing this like uh this, and let me only predict 50 30 words, not too much, so we can do some more testing. So I said we use a fluid grid system to create flexible layout that adapts seamlessly to different screen sizes. And it's working properly here. You can see that adapts seamlessly to different screen sizes. You see, just I assume because it's that's adapt the line is properly working properly. This technique is central to our responsive. And as you can see, this technique is centered to responsive. So model understand what comes next according to this website. What am I putting there? Okay. So now you see this is how it is working. It's working properly. Our small language model. Okay. And this is very small. That's not a big one. And it's working properly for this website. Okay. Let's me move back. And we can, oh, this is some, okay. My name is Bill. Okay. Let me some, okay. Let's try some case studies. Okay. Let's go to here. And let's try some case studies. It should come here. Okay. So, hello, my name is Jimmy. Okay. I don't know how can I copy this. Okay. Hello, my name is Jimmy. Let me copy and paste this. Is it works or not? Hello, my name is Jimmy. Okay. No, I'm not copying exact thing. Hello, my name is Jimmy. I did not put dot, and let's see is it works in that way. Uh, okay, yeah. My name is Randy. I am the CEO at Elsa. My company collaborated with Ali and team at Codexo to develop something really innovative, and we call it. You see, my company collaborated with Ali and the team at Codexo and developed something really innovative, and we call it at Exa chatbot, and it's working properly. And this is the amazing thing what we have built right now. We have trained our own small language model on this website data. Now this is your task. Follow my this tutorial, follow this lecture, build your own chatbot system like simple pre-trained model. Okay. So this is a pre-trained model. In the next video, I will make a proper chatbot like you will properly chat. Hi, how can I assist you? Okay. So I will build properly chatbot, and this is how actually things are working in AI. Whenever the Llama 3 point model, Llama 3 or whatever, OpenAI launch a model, OpenAI actually launch a chat model, not a base version. But there are a lot of open source, the base models are there. Like if I say Llama 3.1 base model, like let me show you how actually the base model. This is how the actually base model working. Like base model has a knowledge of everything. Okay, these are not a chat model. So in next video, I will tell you how we can use these words to train our chat model as well. I should need to see how if like again base. Let me see. Hmm, I think so. I can test it maybe using okay Llama 270 maybe if it's something. It should be. I don't know from where I can see because I think maybe I need to go. Uh, using Llama. I think Llama if it's providing something. Okay, yeah. Here I think this is the base model. I think Llama 270. No, this is the chat model as well, not a base model. Okay. But actually, if you go some website which has a base model, so you can simply go any Wikipedia page and copy the text and put it there. So it will also predicting the next word. So this is how actually the things are working in AI world. Okay, so this is what we have built so far. So in the next video, I will let you know how we can make this model into a chat model as well, and which give us a proper chatting responses. Okay, so stay tuned with me and see you in the next video. Bye bye. Take care.